Okay, thank you very much for everyone to join this call. This is the iNEMI Package Tech webinars. And today's topic is role of EDA in advanced semiconductor packaging. Presenters is Sang-Hyun Lee, Dr. Sang-Hyun Lee from Cadence Design Systems. Let me briefly introduce today's presenters, Dr. Lee. He joins the Cadence last year and is working in development of EDA tools for advanced packages such as 2.5D wafer level fan-out packages, co-packaged optics or SIPs. He has work experiences in Amcor's and Samsung Electronics. He received the doctor degrees from electrical engineering from universities of Michigan. Now, about the abstract, as all of you that advanced packaging with heterogeneous integrations has made one package integrations of multi-chips a crucial part of finding alternatives to transistor scaling. Therefore, complexities and increased number of die-to-die or die-to-substrate interconnections has led to the need for EDA tools that can support integrations of overall designs, planning, implementations, and system analysis in a single cockpit. Dr. Lee will present the advanced packaging technologies trend and provide an overview of Cadence EDA platform that enables seamless design from front ends to back end for the new areas of the advanced packaging. About the iNEMI packaging, the technology group, this is formed by iNEMI members and chaired by Dr. Wekilo from Intel. The iNEMI package technology webinars are organized by this package group. We will have webinars next month, June 28th, from not 18th, 28th, from the 10 p.m. Japan time. The presenters is from Yo, and we'll discuss the advanced package technology trend. We will announce the details soon. Also, you can, about the iNEMIs, you can reach to those peoples or visit the iNEMI website. And end of the presentation, we'll have Q&A sessions, and Weki will lead these sessions. So please use chat box and write your questions there. For presentation document, we'll send an email with URL links, so you can download a copy from the link. Please mute your lines during the presentations. Okay, now let's start. So I will pass to Dr. Lee. Would you start?
Thank you. Thank you for introducing me, Masahiro-san. Let me share my screen. Okay, can you see my screen?
Yes.
Okay, so thank you for having me this opportunity to present here. So nice to meet you. As I was introduced, my name is Sang-Hyun Lee from Cadence Design Systems, Cadence Korea. So today's topic is the role of EDA, electronic design automation in advanced packages. So I will go over with some kind of short advanced packaging trend and some challenges from this advanced packaging era, and what the Cadence can do and support for developing these advanced packages. So first, I will briefly go overview of the Cadence. Cadence is developing computational software, and the yearly revenue is around more than $4 billion. And we have 26 global development centers. So we support all the semiconductor major semiconductor customers with our design systems. Okay, just a moment. Okay. So first, I will start with the theme of ending of Moore's law, or close to the ending. So we have enjoyed the followed his prediction for the past 50 years, but these days it becomes very difficult to catch up with, because both technical difficulties and economical difficulties. So Moore himself also predicted it, and he mentioned some kind of possible solution that to build large systems out of small functions which are separately packaged and interconnected. This is, I think, a brief, definition of our, advanced packages. So then what makes it difficult to follow the Moore's law? And these days engineers are trying to develop a advanced packages. So starting back in 2012 something, early 2010s, the cost per transistor has been steadily rising and prompting many leading edge companies to start investigating alternatives to basing everything on the Moore's law. The cost increase very high as the silicon nodes become advancing. So companies that don't build hundreds of or thousands or millions of chips find it very difficult to recoup NREs, non-refundable, investment at the latest design node. So huge and expensive design teams are also required. So when designing a complex SoC at the latest node. Another factor is the fact that large electrical size chips typically don't yield very well comparing smaller chips, and it of course the low yield means the higher costs. So we saw an example of this with Xilinx around 2008 when they partitioned the large FPGA into 4 small, high-yielding chips and connected the 4 chips together on the silicon interposer, arguably launching the 2.5D IC packaging trend that has become commonplace today for HBM processor integration. And also, we can't forget about the analog and RF. Well, leveraging Moore's law has never been a big benefit, as scaling down in geometry makes some analog circuit more challenging to design. This also applies to today's high-speed IOs, which are closer to analog design than digital. So these are this kind of some major drivers for developing the advanced packages. So for to satisfy these drivers and requirements, we are trying to find a solution from the advanced packaging, and the keyword of the advanced packaging is kind of heterogeneous integration and chiplet or 2.XD, 3D stacking or interposers and TSV, TGV or wafer level process, fan out or bridge RDL. All of these new technologies are required for these new platform, new advanced packaging platforms. Okay. Then what is the difference between the previous legacy packages and the advanced packages? There has been a packages with multiple dies. A long time ago, we already had, some one package with multi dies, but and this was called the MCM, multi-chip module package. But in the MCM package, the dies or packages are loosely assembled. The distance between each, packages or dies are not that, close, because they didn't need any closer, interconnection for that. But as the performance has increased, should be increased, and because of the economical region, the people want to split or partition the die, SoC die, so that they can be made smaller size, and they can be packaged on one substrate with different cores or IOs and memories. But to get enough sufficient performance, they should be very close to packaged, assembled, and the interconnections between these dies or chipnets should have much more than older legacy packages. That makes we need the previously I mentioned the special technologies are required to achieve these advanced packages, heterogeneous integration, the packages. For example, this is a common example of a 3D die stacking package. So one SoC can be partitioned into two like this, and each partitioned die becomes smaller than one SoC die, so that the yield is increased. And also we can use different technologies for these two dies. One, for example, technology A, which has 3 nano and 1.4 nano advanced silicon node can be applied. And for the die 2, technology B, we can use just 100 nano, much cheaper technology can be used, so that we can reduce the overall semiconductor costs. But we don't want to lose the performance, overall performance, by partitioning these one SoCs, right? So we have to consider short wire power and performance bandwidth, all should be considered to achieve same or better performance than one SoC. So to get to develop these advanced packages, we need more than all the packaging technologies, which are mostly based on OSAT, outsourced assembly and test sites, which use all the kind of assembly packaging technologies. But we need to adopt foundry technologies, IC designs, IC packaging, some IC development technology should be applied. So that causes kind of the boundaries between OSAT and foundries, or post process and the front process has merged, and the boundary become very weak. So some for example, TSMC or Samsung Foundry also, they do packagings, and also the OSAT like ASE, MCO, they do develop a RDLs and the assembly 2.5D packages. So all the in advanced packages, the boundaries is very, very weak. Now, to develop these advanced packages, we need to consider something more in various area. For example, in the advanced packaging assembly, we need to develop a process of stacking or hybrid bonding or wafer process, and RDL or silicon bridge new process should be developed and considered. In material, we also need to get this high performance package. We need a new packaging materials for these advanced packages, like new teams for higher summer and PID, photo imageable dielectric, like photo imageable polyimide, which has a higher resolution. And also in the test methodology, so we need to have some wafer level testing technique or high resolution technique. Fine pitch probing also is required. In the design and simulation, so the advanced packaging has much more complex design. So we need to do some automation. We cannot do design with a manual way because it is too much complex, and the co-works between IC packaging and system is also very become important. And as you know, for the advanced semiconductor industry, the TATs, every year they ship out new devices. So the design TAT should be very short so that they can make time to match the time to market. And the system level simulation for overall packaging and system and die, all systems should be considered in the simulation. And for the chiplet and the advanced packaging, they need some kind of a new PHY, new interconnection standards, which has lower power and high densities. So all of these areas we should think about it, and we need to develop for the new packaging platforms. So I will go over with some of the challenges to developing the advanced packages. So first, the design flow challenges. So as I mentioned, the design of advanced package is very complex, very complex. So the number of IOs are increased, and so the performance between the package die and the substrate and overall system is very closely related. So we need to support and design parallelly, so that one part of, for example, die and the substrate do not match in electrically or timing, then the overall performance will not good. So we have to consider all the systems, and the design should be collaborated, and some design tool also needs some new assembly technologies, like stacking and hybrid bonding. So the design tool should be evolved to support these new platform and new technologies. And also in the analysis and sign off, the package becomes complex, so we have to consider many things before designing and during designing and after design. So we do some early stage analysis, and also the final sign off become very important. And for the sign off, it is the very complex packaging, so it takes very long time. So we need to design effectively and efficiently, so that we do not waste time at the final stage. And the ecosystem. So actually, the PDK is the process development kit, and it is from IC side. Actually, in the packaging side, we do not use that kind of term, but the design in the advanced packages, the packaging designers also need to develop a packaging assembly design kit, ADK, so that they can communicate with their customers, or designers and customers, or supply chain engineers, so that they can share their assembly design kit and all the design rules, so that there should be the design time can be very short, so that TAT of designing will be decreased. So these new assembly design kit also needs to be developed in the packaging side. It is very new thing, so we need to consider everything that we need to. And also in the legacy packages, we just collect on-shelf dies or packages and assemble them on a substrate. But at that time, in the old time, it was okay just to connect by the dies or packages and connect them with relatively large distance, and the interconnections IOs is not that high. But in the advanced packaging, the distance between the chiplet or dies should be very close, and the information transfer and should be very large. That means we need lots of interconnections, so that we need new interconnection standards and methods. There are lots of IP companies that are developing that interface standards, and so lot down there are many interface standards which is for the chiplet packaging or advanced packaging designs. And the 3D implementation. So the packages are not the 2D two-dimensional, only there are 2.xd, and the 3D packages are getting popular. So in the design tool, we need to support 3D interconnections and the parallel interconnections, 2D interconnections, both, so that new PDK and new design tool should be developed and applied for designing and developing these 3D the packages. So these the old multi-die system package development, in view of design, we need a good data management system and some additional system level sign off, and for the simulation and the code design is also included in the overall design flows. And in one packages, we may have a digital, analog, or the RF to design. The dies can be integrated, so the design tools for each domain should be collaborated and connected. But in the old time, it was not connected. I mean, the IC designers do their design and toss their text or Excel files with the net list or some information to package designers, and the package designers are designing with these IC informations and design with mostly manually, and after the package design, then these packages are tossed to PCB designs. So there are large words between IC and package and PCB. There is a large and just one way, and the wall which blocks the difficult to communicate each other. But in the advanced packaging, advanced technology, we should communicate and we should co-work, we collaborate, so that if not, in the end, the overall system will have a lower performance. So IC packaging PCB, we need some kind of new integrated EDA solution which connect and communicate, each domain IC packaging PCBs. Okay. But it is not that easy, because each designers for IC designing, for example, IC designing, they have their own tools and their own rules, and the package designers have their own tools and their own rules. So all the information and tools and rules are tangled, very complex. That means it is very error prone, hard to reuse for the next generation platform design. So we need some kind of a single unified design tool which manage all of these tools and informations and the rules, so that makes very simple and less human error and easy to reuse. And also this, single unified design tool should have a well-organized function to perform all the design flows, from planning and designing and the final sign-off. And also it should have, to check the IOs and powers, summer, and so on, the simulation, the functions, and also it is a multi-die system, so it should manage all the area like digital, analog, and the chiplet packaging and PCB, and the new technology should be supported. So we introduced the 3D IC platform. It is industry first integrated and high capacity 3D IC platform, and it enables 3D design planning and implementation and system analysis in a single unified cockpit. So this integrated 3D IC act as a some manager of all the design flows and developing a silicon advanced semiconductor platform development. So this platform and manages all the required design flow by communicating related design tools like Cadence, process platform for analog and customized design, and Allegro APD or PCB designer tool for substrate or board design, and also the simulation tools like for the summer and power integrity and signal integrity and timing and the physical verification, DRC, LBS tool, all the these analysis and the sign-off tools are also linked, and so these all tools will have that their own data and data results, and these data are collected and hierarchically organized in a single multi-technology database. So with this single database, it is very easy to implement a flow, all the the design flows from the scratch to the end. The reason that we could develop this single unified integrated 3D IC is Cadence has all the we are the only company which has all the tools for IC development and IC designing and packaging and PCB design. So we have all the good portfolio, so that we can manipulate all the tools with the integrated 3D ICs, comparing the other EDA vendors. We have a good benefit for that. So this is the our overall kind of, we have much more tools, but these I collected some design tools portfolio for the advanced packaging design. For the IC design, we have Innovus for digital virtuoso, and for RF microwave office and simulation tools. We have a Spectre, Relator, Excellium, and also for the substrate and packaging and PCB design, we have Allegro X platform. And system analysis, we have Clarity, Celsius, EMX. So all of these tools act for developing the advanced packages, and we have all the tools, and these tools are can be managed in one integrated 3D IC platforms. So overall design flow can be divided into three. The first is system level planning. So for the good design, good development, we should have a very good planning. So we need to decide which platform we use. We want to use just simple flip BGA or 2.5D or multi-chip packaging. So we combine all the die information, package information, substrate information, and do some 3D partitioning and flow planning. We do the planning of all the overall packages, how to connect, how to optimize the die to die distance. Everything is planned in this step. And during this planning, we also do early analysis, early summer analysis, and early PI analysis, so that we do not want to waste our time. If the if we find some design flaw at the end, then we need to do from the scratch. It will take much more time, so that we do some early analysis, early simple analysis, so that we can minimize the overall design failure. If after the early analysis specs is satisfied, then these informations are going to our IHA database, and we are the next step. We are doing implementation, actual design for the packages, or digital die, or interposers, and the some analog devices. All the dies are designed, implemented with proper design tools. After all the design tools are finishing the design, then the combined overall system is completed, because we already planned how to put these each chipnets or dies located on the substrate, right? So finally, we need to do final system level overall analysis, and this final sign off for production. So these all three steps are required in designing the advanced packages, and all these three design flows can be managed in one cockpit tool integrated 3D IC. Okay, as I mentioned, there we have three steps in the overall design. Again, so We have a planning and the designing, actual designing. We call it design implementation, and the analysis and sign off. So it first, integrated system planner or Orbit IO is the first tool for planning. And after the planning, each design implementation tools are used for actual designs, and all the designed dies and packages are already connected. Then the overall system level analysis and the sign off is done. Firstly, system level planning. So integrity system planners provides hierarchical planning and the optimization of system level design and connectivity. So it provides chipnet to chipnet and package, and the package to board signal mapping is done, and the early stage thermal and power analysis. These are done by simulation tools, but the integrity system planner calls the proper tools for early simulation, and the stack management can be done. How to step, put the substrate on the substrate with, for example, 0.5D, we put the silicon interposers. On top of silicon interposer, we put GPUs and the HBM dies and so on. Everything is planned in this system planner, and all the dies and chipnets are connected, and the connected checks are done with integrity system planners. And also, we work with a large foundry company, for example, TSMC. TSMC is developing 3D blocks, which is a kind of code-based, planning. So we support this, 3D block code. So our integrity system planner can read this, 3D block codes, then it is automatically generate all the stacks and the floor plans with the 3D blocks. And also we are also working with the Samsung foundries. They are developing a very similar one. It is called the 3D codes. So our integrity 3D IC also supporting that Samsung foundries 3D codes. After planning, we do implementation. So integrity 3D also can do some the design itself with their canvas, and also they do database to the each proper design tools, and all import the finished designs from the Virtuoso and the Allegro for the PCB design, or the substrate design. So all the data are collected in a one database, IHDB, and these all the database data can be loaded in this integrity 3D IC. And also the co-working between the implementation tools, and also between the simulation tool is possible. So Virtuoso or Allegro, as these implementation tools can be co-worked with Clarity and Celsius and Security. So all these tools are connected and can be shared. They can share their database, so that they can simulate during the implementation is possible. We have Allegro-based solution. So actually, I am in part of Cadence Allegro team. So Allegro APD, Advanced Package Design Tool, is worldwide most the design fabs or feminist companies are using this advanced package designer tool. So if we use that tool, that is much more easier to communicate if we are working in foundries or the OSAT, it's much more easier to communicate with the customers if you are using this Allegro-based solution, because as far as I know, more than 90% of our customers are using this Allegro-based substrate and PCB designer. Then which implementation solution is best? So it depends on your idea and your application and your product types. For the digital, we recommend our Innovus and the silicon interposer, Innovus or the Virtuoso, and also for the RDL based design fan out wafer level based design, we recommend use Allegro X. And for the custom IC or analog IC, we recommend the Virtuoso. So all of these digital and the analog RF and the substrate design, all these tools can be managed in the one single cockpit tool integrated 3D IC. As I mentioned, the final step is analysis and the sign off. So for the system level, all the dies and packages are assembled, and the final product, the final system should be analyzed for the power integrity and thermal and the mechanical stress and so on, and timing, and also physical inter-die connectivity should be checked for sign off. We use Pegasus for this verification, TRC design rule check, or the LVS layout versus schematic check. So all these sign off and analysis tools are available in Cadence. And these are major four multi-physics simulation analysis tools for the advanced packaging. So, and clarity for the EM analysis, and Celsius for the thermal and its warpage and stress. So EMX is the extraction methodology solver, and security is SI and the PI solution. All these tools are for analysis in advanced packages. And we are working with major foundries, major and IT companies with this integrated 3D ICs. So with this the single cockpit, they wanna do some design flow development for their own packages. For example, TSMC, they have a Quad or Quad S, Quad L, various design platforms, and they are using integrated 3D IC for developing from the first to the end with integrity. And next, then what is the next for the EDA? We think AI is the next step for enhancing our EDA tools. As I mentioned, I presented, we introduced a single cockpit tool. Then each designers should have easy planning, easier designing, easier and fast simulation. So as I mentioned, the advanced package is very complex. So the design time is very long comparing the all the packages. So AI should be implemented in the design tool, so that helps the for example, auto routing in interposer and auto routing in RDLs in the fan-out packages. That will help the designers minimize their design time or in the designing, and also optimizing in their design. So we are very hardly working on the AI development, and also the cloud services for the customers who is relatively small, so that they cannot use some servers for AI learning. Then we are collaborating with Amazon AWS so that customers can use their servers for AIs to run for the AI for designing, AI designing for the optimization and some routing and actual implementation. So this is the last slide I prepared. So now every companies are looking for good to develop advanced packages for their own purpose. The best way to start, I think, is using very efficient design tools so that they can start planning and the implementation and the sign off. Everything is done in one solution that will give the customer, we think, give the designers the much efficient solution and the time can be reduced for overall workflow. Okay, that's all for my presentation. Okay, if you have a question, yeah.
Yeah, that's good. Thank you very much,
Mhm.
Dr. Lee's impressed. I'll pass to Wiki. Would you lead the Q&A sessions?
Okay. Thank you, Dr. Lee, for this insight about this Cadence design systems and the future looks of enabling the EDA platform to accommodate advanced packaging. So before we open up for question, maybe I just ask a few questions so that we get ourselves warm up in asking the question. I know that with advanced packaging, we are disaggregating the dies into multiple pieces so that we can get a lot better yield from the wafer level, right? Making it small and more cost effective. But between monolithic and disaggregated die design, right? Which one has more room for design optimizations? Like, which one has more, like monolithic and disaggregated die? Which one has more room for design optimizations for the use of the die area, signal, signal routings, and so on?
Well, I think it depends on the application. So, for example, for the 2.5D, it's just the one large GPU. For example, NVIDIA's the AI accelerator. It has a largest ABF substrate and the one interposers, and the on top of the interposer it has a large GPUs, and around the GPU it has 6 or 8 HBMs, right? Yeah. So it is just collector of the required packages, the HBM and the SoC. These GPU is not partitioned, right? But some application it should be partitioned. They try to partition these packages because mostly they wanna have a lower cost, economical. The region is very high. So for the optimization, so it might be easier in 2D because in some case, because it has a large area and they put some their functions in one die, right? But if you split or a partition like here, so we need to consider in 3D way, right? In 2D way and 3D way, we should consider both. We need to think more than that, the 2D. But for the we can use technology, lower technology, or reusing the technology is a very the efficient way in design, right? So for the optimization side, it actually it both optimization is difficult, but it depends on the application, and that's why, as I mentioned, we are trying to adopt AIs AIs that can do auto routing everything, but also it helps to find the optimized flow plan or optimized routings. So with our AI solution, then you don't need to worry about much about the optimization things in the future. Okay.
Thank you. Any question from the crowd, audience? You just raise your hand or ask, or you can type through the chat.
I have one question, Wiki.
No, go ahead, Shuya-san.
When we talked about the design integrations, one of the challenges is the language and communication from the CAD data, but it looks like you communicate quite well. Very nice. So my question is more on the simulations. Now you just mentioned that the routings for 3Ds looks done quite well, but when we think about like stacked or embedded dies into the PC board, then probably the simulations is wondering whether how you could do simulations like EI electrical or thermal simulations to optimize the designs.
Well, so good question. So these days, many packages are stacked. 2.5D or 3Ds. For example, we are working on major customers with the stacked memory, so-called HBMs, right? So it has a base logic die, and on top of that logic die, it has several memory dies, right? And we are doing some 3D thermal and warpage analysis with our simulation tool. These tools developed also we have 3D concept. 3D analysis is possible for all the stacked dies. So that's why we call system level analysis. So system level means all the stacked die can be analyzed in thermal or warpages. So I'm not sure if I'm not a very expert in simulation tool, but I'm not sure if it is a good answer or not. But we provide the 3D solution for the 3D stacked packages too.
Oh, that's great. Thank you very much.
All right, open to the audience to ask questions.
So in the chat, why mechanical stress analysis is not included in Cadence? Actually, the mechanical stress is done by the Celsius. Actually,
So I saw that later on. Yeah.
Yes. So I mean all the packages that the size of package is not that large and they're simple. But for example, 2.5D NVIDIA's GPU, the AI AGB packages, it has the sizes around 55 millimeter, so 50 around 50, very large. So that means that it has a lot of stresses. If all interposers and packages are assembled, then the overall stress is very large. So the stress simulation become very important in developing the advanced packages, and that is it. All the stress is from the thermal, and also because the different material like polymers and silicons are combined, that cause warpage and stress, right? And the also thermal region is also important, and the thermal and work stress mostly warpage the simulation is done step by step mostly. Before assembling the interposer, we do simulation. That at that time, during step by step, we do simulation with input the process temperature. For example, lip flow or die bonding, so that all step by step thermal stress, thermal simulation, and also warpage and stress simulation is done, so that we can optimize the materials and the thickness of metal, but percentage of metal can be optimized. So these days, I think the most important part, especially for the assembly part, the thermal and the stress warpage simulation became very, very important.
Yeah. I was wondering, is Cadence working with the customer to validate all the simulation result, and knowing that simulation can easily get wrong from time to time, and if the assumption is wrong, do you work closely, or there's other group of people do a lot of this validation work?
Yes, right. Correlation between this the simulation result and the actual result is very important. We closely working with big companies, big customers. Yeah, and because of security, I cannot tell everything, but we do. They provide us the data in our secured chamber. Then we do some simulation, and we gave them simulation result, and they do compare. Customers do compare and let us know some result. Some it is matching 5% or 10%. Then we some modifying or some input data and so on. So the cross working with the customer is very important, especially in matching correlation between the simulation and actual result. Thank you.
It's good, Dr. Lee. I think this is part of iNEMI effort also to work with EDA tools and packaging house, material suppliers to derive the methodology and conduct more open validations effort, and more open, because iNEMI is member based, but whatever findings that we have will be published, and then we'll make known to external, so that that will give your company or give the whole methodology more solid ground for validations, and we are hoping for collaborations in the future as well. Yeah, thank you for the answer. Let's we're at the dot, but any last questions from the crowd? Going once. Anyone raise hand, or you can type quickly. All right. Shia-san, you want to wrap up?
Oh, yes. Again, thank you very much, Dr. Liz. We learned a lot from your presentation. Impressed. And as I mentioned that let's do a collaborations with the iNEMI project teams. Thank you very much. And also thanks to the audience. Thank you for joining this webinar. Again, we will have a webinar next month, so please join the webinars next month as well. Thank you, everyone. Thank you, Dr. Lee.
Thank you.
Hey, thank you, Dr. Lee,
Thank
for your
you.
time. You're very insightful. Thank you for your time.
Thank you.
Thank you very much. Thank you, Shia-san. See you.